Let's do number 7. Electron moves with a certain speed parallel to the field. What kind of force does it experience? So this is a case where you are given plenty of numbers that you could plug in the numbers to the equation that gives us the force on a moving charge, QVB sine theta. But the whole point is that for a particle to experience a force when it's moving in that external field, that velocity has to have some component perpendicular to the field. The velocity can be perpendicular to the field. It can be at a certain angle, because when you do sine of that angle, you'll get something that's non-zero. But if they're parallel, then theta is 0, sine of theta is 0, sine of 0 is 0, no force. So see that word parallel? They're moving parallel. There's not going to be any magnetic force on that charge. Number 8. A loop has a current and it's in some external field. We have an area. It's mounted on an axis that's perpendicular to the field, which allows the loop to rotate. What is the torque? So you really have to be able to visualize this, because if you just stick numbers in the equation, it's not going to work half the time, because you've got to visualize the angles. So the way that I'm going to visualize this is I'm going to have my loop like this in the plane of the paper, but it's going to have an axis of rotation, so that the loop can rotate around this axis. So it's, when it's rotating, it's coming towards you and away from you. It's making a little loop here around this axis. So the reason I drew it like this is because I drew the magnetic field going up. So if I did the magnetic field going up, then the axis is perpendicular to the field, and that's how I know that that's how it's going to rotate. So what's the torque? And usually there's always going to be an answer that says 0, because sometimes the answer is 0. But in this case, there's going to be a torque on this loop, because you have a current in here, and let's say the current is going this way. You don't know which way the current is going, but let's say the current is going this way. Then the magnetic moment would be out of the page, which would be perpendicular to the field. So then you know that the loop would actually rotate so that it now looks like this. A flat loop perpendicular to the page, so that now the magnetic moment mu would be in the same direction as the field, while here the magnetic moment was perpendicular to the field. So you know it's going to rotate. But the trick is that it says the plane is oriented at an angle of 25 degrees to the field. So the plane of this loop, and it's hard to draw it. I drew it as though it didn't have any angle to the field, but there's an angle of 25 degrees. And when we're using the torque equation, mu b sine theta, the angle that we care about is the angle between mu and b. So maybe if I draw this a little bit differently, I can show it a little bit better. So I'm just going to draw a different loop so you can see. So if I have a loop which is flat, and so it's in a plane that is perpendicular to the paper, and let's say the current's going this way, then we know the magnetic moment is going this way. And let's say that the magnetic field is going this way. So if this were the magnetic field, then the angle that it would give us here would be this angle right here. This would be 25. Because this is the angle from the plane to the field. That's what it gives us. But what we care about is the angle between mu and the field. We care about this angle. So this angle is 65. So it doesn't matter that I drew it like this over here. The point is that if you're given the angle between the plane and the field, well, mu is always perpendicular to the plane. So that means that the angle that you really need is going to be 90 minus that angle. So you really have to pay attention to which angle that you're given. And once you have that, then it's just a plug and chug. But of course, one of the answer choices here will be where you use 25 degrees instead of 65 degrees. So the numbers that you'll plug in here is, you know that mu is your NIA. So this is going to be the current. This is going to be the magnetic field. This is going to be the area. And we already talked about that the angle is 65. So we have just a circular loop, just one. That means n is equal to 1. So we have NIAB and we have theta. Plug all of that in and we'll get answer B.